Alright, in this video I'm going to talk about using integrals to find volume, and we're going to do this integrating. You can think of this kind of adding as integrating. And so we're going to be using integration to find volume, and we're going to be integrating cross-sectional areas. I also sometimes refer to these as slices of an object. So you can take a slice of it, a very small slice, add up all of those very small slices, and you'll get volume. And you can do that adding, that's why I put it in quotes, by integrating. So essentially, I mean, if you want a formula for this, we could say that volume is equal to the integral of, we could say A, and I don't really want to put variables on this because sometimes our area will be a function of X and sometimes our area is going to be a function of Y, and who knows, maybe we want to define it with some other variable, but I don't necessarily in this integral want to kind of put a specific variable in there. All right, so, and once again, I just want to kind of say, every time I say add, that we're going to add, what I mean is that we are going to integrate. And what I mean by these slices, I mean area, I mean cross-sectional area, and that's what we are going to be integrating to find volume. Let's do an example. Let's do a few examples. For the first one, let's find the volume of a circular pyramid of height 12, let's say 12 meters, why not? And a base with a radius, since it's circular, of 3 meters. Okay, so once again, we want to add up areas over the height. So I'm going to draw this circular pyramid. So it's a pyramid, but it has a circular base to it. So here's my pyramid, circular base. The height of it, so from right there to right there, height was 12 meters, and the base had a radius that was 3 meters. Okay, so what we want to do is add up slices. So I'm going to draw a slice, and I don't want to draw it at the bottom, I don't want to draw it at the top, I want to draw it halfway in the middle so I can get an idea of exactly what I would be adding up. So here is a single little tiny slice. It's got a little tiny depth to it. And this little tiny circular slice. Now notice that as this slice, if we moved it up, the radius of it would decrease. If we moved it down, the radius would increase. So this slice does not have a single radius. The radius actually changes throughout it. So let's call that radius R. All right, so now what we want to do is we want to add up the area of that slice. And we know that the area of a circle is pi r squared. Okay, so we could say that, and that would be fine. We could integrate that, but we don't exactly, it's hard to tell exactly how our radius is changing. And so we want to change this into a variable, and because we're adding with height, so notice that this actually, if we looked at this slice, it would increase, it would go up, and it is with respect to height, and normally we consider a vertical axis to be y. What all of this means is that with this integral, I I want to integrate with respect to y. And that is again because we're integrating with respect to the height. We are adding up these circles over height. So we're adding them up over y's. Okay, so to start out with this integral, I can integrate from 0 to 12. I'm integrating for 0 to 12 because I know that this thing is 12 meters high, and that has to do with the vertical axis. That has to do with y's. So here's part of it with y. And I want to integrate pi r squared, but I want my function to be in terms of y and not in terms of r. So here's what I'm going to do. I'm going to draw another little picture down here. I'm only drawing half of this. Its height, sorry, that was me dropping the pen. Its height is 12. This base would be 3. Here's my little section right there that is r. And y equals 0 is at the bottom. So every time I move up a distance of y. So if I go to right there, that distance would be y. So if I then take the full height and subtract that distance, the distance from the top of this to my radius, or to my slice, would be 12 minus y. Now this is a little tricky. You could have picked y equals 0 at the top of this, and you could have defined this differently. So just kind of keep that in mind. All right, so similar triangles here. If I do the full height, so full height is 12 to the full base, which is 3. That is in proportion to the height of the smaller triangle, which is 12 minus y, divided by the radius of the smaller triangle, or the base of the smaller triangle, which is r. I'm doing all of this to get r in terms of my function y. So my radius is going to equal 12 minus y over 4. Let's make sure I did that right. I multiplied by r, that's 4, and I divided by it. Okay, so my radius is equal to 3 minus y over 4. So my radius is equal to 3 minus y over 4. And I'm going to integrate that with respect to y. Okay, so I just want to clarify before we integrate this. All of my variables are in terms of y here. I have y. All of this work down here at the bottom was to determine the radius in terms of y, because I wanted to add up the pi r squareds, but I wanted to add them over y's, and I needed the same variable. I need y there, I need y there, and I need y in the bounds. So I had to change the radius and come up with these similar triangles to change the radius to y's, and then I could do pi times that new radius with y squared. That's in terms of y. My bounds are in terms of y. Okay, hopefully that clarified. And I think we can now integrate. All right, so what I would do with this is this is going to be a little kind of u substitution here. I would do 3 minus y to the 4th. I would add 1, divide by that number. Now when I integrate, I also need to divide by the derivative of the inside part. The derivative of that inside part is negative 1/4. And I need to integrate this from 0 to 12. Hopefully that wasn't too confusing. If you found that too confusing, just do a u sub. The other thing you could do is square that whole term. You could multiply it all out and then integrate that. We should get the same answer. Okay, so I've got negative 3/4 in the denominator. That's the same thing as negative 4/3 in the numerator. Oh, I've got pi up there too. Maybe I should, I'm gonna put that pi also outside. So I've got negative 4/3 and pi all in the numerator. Plug in 12. I'm plugging in 12 into this term. 12 divided by 4, that would be 3. 3 minus 3, well, that's 0. Minus, when I plug in 0, I get 3 cubed. Okay. Negative times negative is a positive. So positive, which is good. We're finding volume here. If we came up with a negative answer, then something's got to be off. One of the 3's will cancel. And 3 squared is 9, and 9 times 4 would be 36. All right, so my volume should be 36. Oh, I guess we started with meters. Let's go ahead and I'll include a little meters cubed in there. Oh, what happened to my pi? How about we do 36 pi meters cubed? Okay, there, that's much better. Okay. So again, we're going to find volume. I'm going to find volume of solid with a base that looks like y equals the square root of 4 minus x squared. And cross sections perpendicular to the x-axis are squares. Okay, so lots to do here. We got to figure out what this base looks like. We have to figure out exactly what we're adding up here. We're adding up squares. So that's going to be the base times height is the same for area. So we have to find that area of each cross section, and then how that relates to the base. Okay, so the first thing I'm going to do is I'm going to draw a picture of this base. So I've got y equals the square root of 4 minus x squared. If I square both sides, I should get y squared equals 4 minus x squared. And then if I add x squared to the other side, I get y squared plus x squared equals 4. Okay, that's a circle. Hopefully you can recognize that as a circle. So that is a circle. But we're only looking at part of the circle. We're only looking at the part of the circle where y is positive. See how there's only a positive in front of that root? So we're only looking at the top. Oh, I already have x in there. We're only looking at the top half of a circle. Okay, so there's my base. Now cross sections, so kind of taking care of this part of the problem. Now cross sections perpendicular to the x-axis. I'm going to draw a cross section in there. So cross sections are perpendicular to the x-axis. So I go to the x-axis and I draw a line perpendicular to it. So there's a cross section, and those cross sections are square. So if I looked at this thing sideways, the red cross section, it would look like that. So where, you can pick any side of this, where that side of it is right there, and the other part of the square is coming up out of the paper, out at you. Okay. All right, we need area. So the area of this is going to equal, well, each side squared. So what do we want to call the side? I'll call the side L. So it'll equal L squared. Right there is L. Now, somehow now I need to relate this area back to the base and back to the problem that I'm working with. Okay, so let's kind of change thought processes and figure out what we're going to integrate with respect to. Now remember that we're going to integrate by adding up these slices. So if we are going to add up these slices are all along the x-axis. So we would take all these slices, they're along the x-axis, and what that means is, I'm going to circle it up here, dx. We need to add up along x's, so I need everything in terms of x. So somehow now I need L in terms of x. Now L, notice it'll change as x gets bigger here, L gets smaller, but then so does our y value. And as we go this direction, L is going to get smaller this way, but so does our y value. And in fact, L really is equal to y. You can always call a distance from the x-axis up y. You can always do that with all of these problems. Okay, so L is equal to y. So the area, being L squared, is actually going to be y squared. And y, we were given y up in the beginning of this problem. Y was equal to 4 minus x squared, the square root of that. And we're going to square all that, which will get rid of the square root, and we'll be left with 4 minus x squared. Okay, so we found an area in terms of x. We're integrating with respect to x, so we want to add up. We want to integrate the area, 4 minus x squared, with respect to x. Now the bounds. So remember that we're integrating with respect to x. Let's go back to our picture. The bounds have to go from, let's see, where is that? This is a circle with radius 2. So the bounds are going to go from the x equals negative 2 to 2. And I would notice that we could use symmetry here. Our heights are the same over both, and it looks the exact same on the left as it does the right. So I could change this integral and maybe make my life a little bit easier by taking 2 times the integral from 0 to 2. 4 minus x squared dx. You don't have to do that, but I like to plug in 0 instead of negative 2. Okay, so this is going to give me 2 times the integral of 4 is 4x. The integral of x squared is x cubed over 3. And we want to evaluate this from 0 to 2. So this will give us 2 times 4 times 2 would be 8, minus 2 cubed is 8, so 8/3, and then we plug in zeros there, and that would give us, zeros. So let's see here. What do we need? Well, common denominator of 3, I guess. Okay, so let's do 2 times 8 times 3, which would be 24, minus 8/3. And 24 minus 8 would be 16 thirds, and 16 times 2 would be 32. Were we given units? Nope, no units, so I don't need to add those. I think we're good. Okay, so on this one, the cross sections were perpendicular to the x-axis, I had to draw the picture of my base. I had to draw a cross section in there. Then with that cross section, I had to figure out the variable that we were adding, I kind of put that in quotes, that we were integrating with respect to. So I knew that was x. I needed everything in terms of x. I had to go back to my cross-section and look and figure out how to get the area of that cross-section in terms of x. Once I had that, I used symmetry to get the 2 times the integral from 0 to 2 and integrated. All right. So a little summary here, or maybe some hints or some things to think about. So first of all, draw a picture. Once again, draw a picture. Figure out what the thing that you're trying to find looks like. Second of all, what variable are you integrating with respect to? What variable are you integrating with respect to? And this is going to be the same variable as the direction of adding the cross sections. So direction of cross section addition. So it'll always be that same variable. And then you also need to find a function for the area of the cross section. And your variable needs to be from number 2. It needs to be in terms of that variable that you find that you're going to integrate with respect to. So variable, well, let me just write, variable is from number 2. Variable is from number 2 on this list. Okay, so what variable are you integrating with respect to? What's the area of your cross section? It needs to be in terms of that variable. And at least for me, I have to draw a picture. I have to draw a picture to figure out which variable I'm adding with respect to and what my area looks like.